Welcome to our fifth lecture. Here talking about how do we move through this engineering design process. First, we spent a lot of time earlier in this course trying to understand how do we analyze problems and how do we try to get down to the root cause of why this problem exists. And ultimately, we try to come up with many different solutions and try to rank or order them of good solutions versus better solutions. One key idea for this is how we try to quantify how good a solution is, and in a very multifactorial, a very nuanced way. It's rarely just one indicator or one criteria that makes a solution good or bad or better. And we look at this today, trying to get a better handle on how do we evaluate all the different ideas that we might have about our final project and look at this idea of key performance indicators. Now, to a little bit of review, we as engineers, we use this so-called cyclical engineering design process to solve problems. It's what we call a heuristic model, meaning that it's not an exact series of steps that must always be followed, but it sort of provides a guideline of how we orient ourselves and guide our process of identifying the problem and ultimately solving it. In many cases, the first thing that we do is we recognize that there is a need for some sort of product or service, that there is a problem that exists. It's important that we define exactly what that problem is. We want to make sure that whoever is affected by this problem has the opportunity to express why does this problem exist, what's the biggest part that bugs them, what do they actually need what do they actually need to be solved, rather than us as engineers assume that we know what this problem is. So we do a lot of research to define this problem, and ultimately we dive very deeply into the fundamental causes and effects. In some cases, it might be something that is physical in nature. We need to apply our sort of general tools of physics and chemistry, maybe a little bit of biology. In many cases, it requires a lot of analysis and logic, trying to ask a lot of questions to interrogate why does this problem exist? What's the biggest cause or driver of it? From there, of course, we do sort of the creative and in many cases the most fun part of engineering, which is brainstorm potential solutions. This is something that many of you will, if you have not already begun on your final project, will be entering this phase very soon. But this brainstorming, while it's fun and is an opportunity for creativity, ultimately has to be narrowed down and has to be as efficient as possible. Our time as engineers is limited, and we want to be able to solve problems in a timely manner without wasting too much time or too many resources. Some of the biggest challenge is trying to figure out how do we test out these ideas. We rarely have enough time or money to be able to implement every potential idea and see what sticks. We really have to be able to predict which the best option will be. And that requires us to be able to either prototype or simulate with a computer model, with sort of a physical model, whatever it might be, some sort of potential solution. We then test it. A lot of this requires us to indicate and understand what does a successful solution look like. How do we define that? Something we'll talk about today. We then sort of go back and forth between our solutions and the results, trying to interrogate how do we make this better? How do we optimize its performance? And ultimately, at the end of the day, and what we'll do at the end of this course, is to present our solution to whoever is affected by this problem. Could be a client, could be a customer, could be someone who are just trying to help. All these things are very important for our job as an engineer, and we as engineers cannot just pick and choose. We must be able to do this entire process. Now, the very first part of this course we spent under this umbrella, which I call engineering analysis, and this is largely trying to understand the problem, who's affected by it, who's part of the decision making around this problem, and why does this problem exist, what are the main causes and effects. We're going to be getting into this week, and of course continuing on the next few weeks as you move through a parallel process for your final projects, is to try to model and optimize these different solutions, ultimately trying to find a better versus worse engineering solution. This process of narrowing down all the different solutions that we might brainstorm For engineers, is inherently a quantitative and metricized process. We do so not with sort of a general feeling. We want to assign numbers wherever possible to rate or rank or measure something about the solution. And it's also a metricized process. We create different categories, different metrics that allow us to fairly compare and objectively compare different solutions. One thing that we'll use and we'll talk about in this first portion of the lecture is this idea of key performance indicators, sometimes called KPIs, and trying to figure out how do we create these different metrics, these different criteria with which we will evaluate solutions, and how does that tell us what makes a good solution versus a better solution. And then finally, in sort of the second and third little videos today, we're going to talk about how do we test those ideas? How do we use this KPI concept? How do we use these metrics to guide a decision-making process of which solutions seem more promising? And ultimately, how do we iterate and optimize those processes, targeting, in many cases, these KPIs? Now, KPIs, key performance indicators, you may have come across in other fields that other people, other disciplines might use them. They're often used in business. They're used in education as well. And engineers make a liberal use of this idea of a key performance indicator. These key performance indicators, KPIs, are as often as possible quantitative, meaning there's a number that can be assigned. It's often a variable, something that we can measure through experimentation. But quite often, these KPIs might be more qualitative. They might rate how satisfied a customer is with a product, or what people feel about a particular political candidate. These qualitative KPIs, in which you sort of rate a feeling or some sort of impression of something, we can still provide a numerical relation or a rating, a scale of 1 to 5, ranking out of 10, so on and so forth. In each of these cases, we create these metrics so that we can measure something about how well our system or process or organization, how well something does a task. Ultimately, these KPIs are not something necessarily engineers generate on their own. We often have to work with the end user, might be the customer, whoever is affected by this problem, to define what's important in a solution to you. What do you care about? How do you define a successful solution? Going back and forth with the end user or the customer, the person affected, generates these KPIs, and quite often we can set some specific thresholds or goals. An improvement by a certain amount, an increase in revenue by a certain dollar, so on and so forth, and create different goals for ourselves. A minimum a minimum baseline. All solutions must meet this minimum improvement. Some expected based on sort of what we think we're able to do, and maybe an ambitious goal. This process of creating KPIs helps us ultimately be better engineers. One, it tells us what does a successful solution look like. It helps guide our process of selecting a good solution or a better solution, and then continuing to iterate and optimize it. We as engineers want to know what we're working towards. We want to know what we're improving and if we're getting any better. KPIs, key performance indicators, is our way of trying to turn something that's potentially very qualitative, very subjective, into something that's much more objective. Commonly in engineering, the KPIs we most often see relate to a few different categories. Cost and economics, how much money a solution will cost a client or the engineering team, is usually the biggest concern. We are a world that works on money in the exchange of goods and services, and so the cost or economics around a solution are very, very important. There's often a finite number of resources available to us. This might be time. Our factory might be only so big and can only fit so many machines or different processes, as well as labor. People require money, and they should be paid very, very well for what they do, but it is very expensive, and being efficient with that labor is often the second biggest concern. As well as, now that we live in a world very much aware of the finite natural resources around us, trying to be efficient and cost effective, as well as effective with the materials that we use to create solutions, to create products, and what waste we generate, the material input to our solution and output by our solution, is very important. And then finally, the realm of engineering that is very human focused and human centered often has to deal with a perception of quality. How satisfied is a client with this particular solution? How satisfied is this doctor with how this medical tool looks? How satisfied is this child with the playground that we've designed for them? These things, of course, engineers spend a lot of time trying to understand and create good metrics around. When do people think something looks good, feels good, is good? How do we make these good KPIs? Now, there's many different philosophies around this, and this is just one approach to it, but one that I have used quite widely in my entrepreneurial time, in my days in business, trying to uh, execute and employ, or rather deploy, different solutions in an engineering sense. So, how do we make a good KPI? You may also hear another acronym as you move through engineering, and particularly the business world, which talks about SMART criteria or SMART goals. SMART is an acronym, as you might glean, that is a guide to how we define or create a good KPI. We could also use it to create good goals or objectives for a particular project. This SMART acronym stands for S, standing for specific, meaning that our KPI, our criteria, has to be very specific, not ambiguous or open to interpretation. The more specific, the better. It's more useful and it's more helpful to define uh, a, a KPI about improving efficiency as improving the number of pizzas produced per person per hour. The more specific we can be, the more exact about what we are exactly measuring, the more helpful and more useful these KPIs would be. So we want to be very specific as we can be. We also want to be measurable. As we said before, these KPIs are all based on some sort of quantitative evaluation and quantitative optimization. Of course, this might be some sort of normal scientific unit, pounds of the pounds of beer produced per batch, or rather the gallons of beer produced per batch, the length of time someone has to wait at a stop sign or a stoplight, so on and so forth. We can sort of measure things using very standard scientific units, but of course we can also try to turn something qualitative, like a perception or an opinion of something, into a semi-quantitative rating, something like a score of 1 through 5, quite commonly seen. A stands for actionable. We ultimately want to set KPIs around things that are really under our control. A lot of the risk and variability in our solutions and in the problem we're trying to solve are really beyond the control of our customers and certainly beyond the control of our engineers. In many cases, you may consider something like, the cost of a raw material being quite important to the economics of producing a particular electronic device. Unfortunately, things that we can't really readily control are sort of global economics and trade, the sourcing of rare minerals from the deep ocean, from asteroids and things like that. There are many things that we cannot control and really are not useful for us as engineers to focus on. We as engineers want to focus on something that we can affect and we can control. Even though we cannot control global supply around a precious metal used for an electronic device, we can control, the choice between a precious expensive metal or something much more commonly found, much more reliably sourced. So we want to focus on goals, on criteria, on KPIs that we can actually do something about, not something that's beyond our control. R stands for relevant. This may seem pretty obvious that our KPIs should be directly related to the problem, and often KPIs are generated by the person affected by the problem. But it's also helpful to create KPIs that are easily comprehended. What I mean by that is that any metric we use, it's helpful if it's an existing metric that people already talk about. We'll see in a moment a KPI related to the gross margin of a business. And the gross margin is an existing term, an existing metric in finance and business that makes it much more easy for people to understand and much more relevant to the end user who may already be engaged in this type of financial metrics. Finally, the T in SMART stands for timely. All the goals we have are going to be deadlined and time frame set, meaning that we don't generate ambiguous goals that should be finished at some point in the future. We create deadlines and we set sort of the range of time we're looking at. We want to optimize the performance of this, the number of units delivered per month, not just the number of units delivered by the entire business over the entire life cycle of it. It's much too large of a time frame. And we also set deadlines for when we want to accomplish things and when it matters that we finish things. So we want to make sure that time is factored into our KPIs in some manner. So these are pretty ambiguous, and as I said before, a lot of the engineering process and what you're learning in this class is very much learning by example and learning by doing. So to sort of give you an idea of how we might use this SMART acronym to identify better KPIs, let's take a look at a few examples. Let's consider and let's pretend that we're being asked to help the Bunker Hill Community College Cafe. This is that little quick serve or sort of grab and go station in the B building, right in the lobby where all of Student Central is. And it's a cafe that provides food, drinks, beverages, snacks, so on and so forth. For this cafe, which does operate as a business, what's important? Well, if you were to ask the people who run this cafe, as well as the students who use this, you'd likely come up with the importance of financial stability. This cafe should be able to generate a net positive revenue, or at least be financially self-sufficient, and should not be in danger of going bankrupt or closing. All things related to financial stability. Of course, the other thing is much more qualitative. Financial things are very quantitative, based around dollars and cents, but something like student satisfaction, how people feel about this cafe, about the options and the pricing, is much more qualitative, generated by the students, of course. Interrogating both the people who run this cafe and the students who use this cafe, you might come up with a few general KPIs to begin with. The cafe itself would obviously care about the balance of the cost of labor, how much each worker is paid, the cost of all the goods and equipment and maintenance, the money spent on the business, versus the amount of money, the monthly revenue earned by the business, how much they make versus how much they spend, a key important part of financial stability. But students may have a different set of KPIs that are a little harder to measure, but equally as valid, equally as important. Students might have a rating system. They might take a survey and rate the Bunker Hill Cafe throughout the year. And they may care about other qualitative things like the number of healthy food options, all which could form potential KPIs, key performance indicators. Now try to abstract these as SMART KPIs, ones that are specific, measurable, actionable, relevant, and timely. We might go through this sort of process. Let's take a look at that financial stability one, at sort of the revenue versus cost. A poor KPI, so one that doesn't really help us do our work as engineers, might be something very vague, like the KPI, the indication of this business, is how much money they make. This is obviously sort of a goal, a criteria, but not a very insightful one, not one that can help us do a lot as engineers to improve how much money they make. A better KPI might be the monthly gross margin measured in percent, which is a function of the operating cost minus the revenue divided by the revenue, from pre-packaged foods, things like drinks or prepackaged sandwiches, snacks, things like that. Why is this a better KPI? Well, looking at our acronym, this goal, this KPI, this indicator of performance is specific. We break down the revenue, we break down the costs by category and subcategory, distinguishing it from fresh foods or things prepared on site. So we break down into a specific subcategory that might give us indication of different streams of revenue and how they affect the business. We also make sure that this is measurable. we create a metric, this gross margin, that's measured with percentage, and we can tell numerically and objectively if our gross margin percentage goes up, it becomes better. If it goes down, it becomes worse. We have an objective quantitative measurement of how well this KPI is doing. This is actionable. Both the operating costs, how much money the business spends, and how much revenue, how much the business generates, are something that can be proactively affected by decisions made by the company that runs this cafe. So we set this metric around something that the cafe can do something about, how much it spends and how much it earns. And we also make sure that it is a relevant metric. So we use this idea of a gross margin because it's a very commonly used metric in financial accounting and small business, and so it's widely recognized, and people understand what this gross margin means without us having to explain a whole lot about it. Finally, we make sure that this is timely. We don't want to just say how much money this cafe makes over its entire lifetime, over some unspecified amount of time. We want to sort of set a time deadline that will measure the gross margin, the amount of money they make each month, and we'll use that as our metric, and we'll use that in a timely based metric. Why do we need this smart KPI? Why do we need this better version of a KPI? Well, ultimately, this KPI, trying to measure how much money the cafe makes from prepackaged food per month, tells us, one, how does our product or process, in this case our cafe, currently perform. It sets an idea for what's a reasonable goal for improvement, trying to say that we will increase this gross margin by 10% is a much more reasonable goal than saying that we will triple the gross margin in a month. It also tells us exactly how we might do that. Again, we try to build in an actionable component to all of these smart key KPIs. We try to set up these KPIs before we begin doing any work, before we begin brainstorming even. If we have these KPIs in mind, it can help us focus our brainstorming, focus our ideation to make us a little more efficient, to guide us towards better, more helpful solutions. With these KPIs in mind, it helps us figure out what is the current state of affairs for this cafe, what's the current monthly gross margin. You might do an analysis, part of your engineering analysis and defining the problem, and find that this cafe currently operates at a gross loss, minus 10%, spending more than they earn. It tells us what's the reasonable goal for improvement. At bare minimum, to have a successful outcome for this KPI, we will need to increase this gross margin to a break-even point, 0%, in which we're spending the exact same as the amount we're making. No one's making any profit, but we're not losing any money. An expected or sort of target goal would be to have a slight positive gross profit or gross margin. Since the gross profit really only accounts for operating costs, but doesn't account for things like equipment purchases, maintenance, other sort of fixed costs that are not related to the day-to-day, having a little bit of extra gross profit helps to cover these additional costs. And then a stretch goal, one that we will work towards, but it is certainly recognized to be ambitious, is to generate a net positive revenue, and we can set a measurable quantitative percentage around each of these goals for this KPI. To get from our current state, let's say of being having a net operating loss to a positive revenue, we can look at the KPI directly, and it gives us insight and guidelines on how we achieve those goals. We see that the gross margin comes from two different factors, the operating cost versus the revenue. And so we might focus our brainstorming, we might focus our ideation on things that target lowering this cost or increasing this revenue. This is not to say that there aren't other things that might affect this KPI, but we can recognize that other types of solutions, things that would be nice to have, like increasing health benefits for the workers, are going to be less impactful to this specific KPI. We might include other KPIs that contribute to worker satisfaction and student satisfaction, but these types of solutions are not going to improve this particular KPI. In the next video, in the next section, we'll look at what do we do with this concept of a KPI to try to build a model that helps us, one, evaluate the current state, as well as figure out what we can do about it.